Okay, time to get started. So, real quick reminder, don't forget, attendance quiz. There's the attendance code. Make sure to do that. Clock's ticking. You got less than 2 minutes left to get that in. Further reminder, don't forget, you have to come up with some sort of an organizational system of reminders or alarms or buddies or whatever to make sure that you, in fact, do remember to get those attendance quizzes done. Attendance codes will always be on the board, etc. Another quick reminder while we're at it. Don't forget we have an exam coming up next time, right? So today is Tuesday, next class meeting is Thursday. We are going to do something by necessity. Oh gosh, I wish there was a better solution, but we are going to spend 50 minutes of the class meeting doing the exam, and that remaining 25 minutes we desperately need so that we can cover material, so that we can finish the material of the course. So, just like Section 1 has a 50-minute class meeting. They take a 50-minute exam. Likewise, y'all will also take a 50-minute exam. By the way, they are different exams. Again, fairness issue. Okay, alrighty. So all of that said, here's where we were last time. So we were talking about the chain rule and how to use the chain rule and things to watch out for when you're using the chain rule. So we talked about this example right here, right? And if you take that example and sort of, diagram it out, right? At first, this is what you get, and this is what I discussed last time as being kind of a bunch of nonsense, right? That's not a composition of functions. The chain rule that we have ultimately derived entirely from this idea of composition of multivariable functions, right? So in other words, the target of the first function being exactly the same as the domain for the second function. And you can always represent compositions of functions with diagrams, but not every diagram represents a composition of functions. Okay, so we have to watch out for stuff like this. We don't really have a chain rule to address that problem. Okay, so what we talked about last time is how we can fix it. And I'm going to, back up to this diagram. I'm going to think kind of wish list time. Wouldn't it be nice if there were a variable right there? Because then I could say, oh, well, these are the sort of the three spaces, and I've got a first function that goes from the first to the second, and the next function goes from the second to the third. Boom, composition, chain rule, we're in business. If only we could dream up some way to make that happen, or we could actually have a variable there where, in fact, as it stands, there isn't one. Right? So the solution that I proposed along those lines is to just kind of do it. I'm going to call this new variable x1. I'm going to make it equal, I'm going to call it x1 star, It's going to be really just x1 kind of in disguise. Now, to say it properly, this new variable called x1 star is a function of x1 and x2, as it must be. And it's, as it turns out, a very convenient and simple function of x1 and x2, and the formula is just x1. Right? So, nevertheless, it's a function of x1 and x2, and so there you go. Now, how does that affect the rest of the equations? Well, you might be particularly concerned about this one that currently has z1 being a function of these variables. I mean, that's what we were given. So, look, I can't actually change the significant meaning of the question that was given, right? So how can I sort of adapt within the rules? Well, conveniently, because colors, I'll use purple, because x1 is equal to x1 star, I can just kind of replace this equation with colors. With this equation in purple that has z1 now as a function of those variables. The only difference is I replace x1 with x1 star, which is x1. So it's okay. It doesn't change anything about the actual sort of, given of the question. It just changes the way in which we write what we were given in the question. So what I've done here is kind of reframe the question without changing any actual particular important aspects of the question, but reframing it in a way that makes this all play by the rules, right? So you make these changes. Again, that equation's out. This equation is in. This then is our diagram. It's a composition, no problem. There's the first function. Here's the second function. Go about your business. Right? So now, if the question is to compute the partial of z1 with respect to x1, all right, cool. Go ahead. All right, chain rules. We got 3 different paths. There's what you might call the x1 star path, corresponding term. Likewise, the y1 path, there's the y1 term. There's the y2 path, you get the y2 term. Off you go. All of these partial derivatives can be computed. Notice the explicit equations that you would compute those partials from are all, again, in the givens of the question. And so, go ahead. All right. By the way, if I remember correctly, sometime very recently, and I want to say it might have been last semester, I wrote an exam question that was modeled off of this example. So I think that would be a really nice example to look at. But by the way, this is not a coded subtext of, it's going to be on the exam. I haven't written the exam yet. I don't know. But I'm just saying, if you find this a little confusing, that old exam question from, I think, last semester, might have been 2 semesters ago. I'm 70-30 that it was last semester. Be a good one to look at, right? And try it yourself first. And then when you've done what you can do on that question, then look at the solutions. And that'll be a good little learning moment. Okay. By the way, notice one of these partials is easy to compute. After all, super simple formula for x1 star in terms of x1. So that partial there is just 1. And thus the rule changes, or the equation changes to this. Okay. All right. Moving along. Let's talk about second derivatives. So sometimes, as you know, we want to talk about second derivatives. When the chain rule's involved, how does that work? I'm going to show you how to do this by way of an example. This is a case where I think just kind of seeing an example and getting the hang of it and noticing some lessons along the way is better than trying to set up an official formal framework. I think, let's just kind of do one and see what happens. So I'm just going to dive right in to this example. And let's see here. For the moment, let's pay no attention to this. We'll come back to this in a few. For the moment, let's just entertain as written here that we have z is a function of x and y. And it also says here r and theta are the usual polar coordinates. And let's remind ourselves, what does that mean? Right? Polar coordinates, different way to think about polar coordinates. Sometimes we like to think of it as, sort of geometrically. But remember, I like to think of polar coordinates as being a function. Right? It's a function that gives x and y in terms of r and theta by standard established formulas that you can then interpret geometrically. Yeah, fine. But fundamentally, let's think of it as a function. So boom, there you go, polar coordinates. All right, so that having been given, the question is to compute a second derivative of z with respect to r, but again, second derivative, not just first derivative. Okay. All right, so as you might expect, the first thing to do is compute the first derivative. Chain rule. 2 paths, 2 terms, the usual. No tricky curves on that one. Right? It's exactly what you'd think. There are a couple of little freebies here. If you want to think in terms of, how do I compute the partial of x with respect to r? How do I compute that partial right there? Well, we have the formula. X is r cosine theta. Right? So what's the partial of that with respect to r? Well, that's just an easy calculation. And likewise over here, partial of y with respect to r is sin theta. Okay. Now, reminder, we're looking for the second partial. We're looking for the r partial of the r partial. All right. Well, so again, then the r partial of the r partial that we just computed, which, just to plug it in, is that. Okay, and again, taking the r partial of that. Okay, now there's a real quickie little observation that I'm going to make before we get into the real tricky stuff. First little observation to make is that because we are taking an r partial, r being there, partial derivatives, you recall, being defined as, well, you look in that world where the variable is that you're taking the partial with respect to, and all your other variables are constant. That's what a partial derivative is. The other variables in its world are constant. That tells me that as far as this calculation here is concerned, theta is a constant. Okay. Well, if theta is a constant, then cosine theta is a constant, and sine theta is a constant. And when you have constants, you can factor them out. I missed. Lost track of where I was. There you go. Factor them out like so. They are, in fact, just constants. Everybody good? All right. Now it's where it gets weird. All right. Okay. How do we make sense out of this right here? Partial of zx with respect to r. And the problem is that it looks like we're taking a partial of a partial. It's tempting to just call that a second partial. It's tempting, for example, to call that. By the way, let me put a big X on this because I'm about to write down a bunch of garbage. Just to show you what garbage looks like. It's good to know what garbage looks like, right? Zx, and we're taking the r partial of that x partial, so it's tempting to write that as zxr. And again, I emphasize that's garbage. You can't do that. Let's take a moment to dwell on why you can't do that. Why is this nonsense? Well, because z is not a function of independent variables including x and r, right? If you look at how how z is defined, is z explicitly a function of these four variables, and which would need, of course, to be independent? Nope, it's not. Right? Z is a function of x and y. So, saying you're going to talk about the x partial and the r partial of that, it's I don't know what you mean. Which function are you even talking about that's defined in a way that would make that make sense? So, you can't do that. Please don't do that. Okay. Let's see here. So, what are we going to do instead then? And that is, come back up here. And here's the big realization. This is the first big trick. The first big trick I want to propose when you're talking about doing second derivatives with a chain rule. First big trick is to realize that if you have a function of x and y, then so are its partials. You can think of the easy examples. Just, think of imagine you have some big expression involving x's and y's. Now imagine what it would look like to take the partial of that, let's say, with respect to x. It's going to be another big expression in terms of x's and y's, isn't it? So it's a function of x and y also. So that's what I had covered up here. That's what I wanted to be the dramatic reveal. Because z is a function of x and y, zx and zy, likewise, are functions of x and y. And let's indicate thusly on the diagram. That's one of what I think is really the big working sort of practical, how you think about it, big tricks of how to do second derivatives with the chain rule. It's just don't forget that these partials that have showed up in your calculation can be interpreted as functions. Put them on the diagram accordingly. All right. The next big trick that I'm going to mention is not really new, but it's don't forget to rely on the diagram. The diagram tells all. Right? The diagram will guide you if you interpret it appropriately as to, what should you do. And so in this case, now notice we find ourselves looking at, let's see here, I need the R partial of ZX. Well, there's ZX. I want to take the partial with respect to R. Okay, well, there it is. And check it out. I have two paths. There's what you might call an X path. That gives me my X term. There's what you might call the Y path. That gives you what you might call the Y term. And altogether then, that partial, by way of the chain rule, just a straight up application of the chain rule. Now that we've got our diagram appropriately appended, now that we're interpreting appropriately, straight up application of the chain rule. There you go. Now this is kind of the critical moment, so let me pause on this. How are we doing? Anybody have any questions about that? Okay. Yeah.
With the partial derivative of x5, can we see it or y?
Partial what now?
Like the partial derivative x, like the second term, not the second term, the second component of the term.
The partial of x with respect to r.
Is it like kind of a conversion factor almost?
I mean, there's a million ways to think about partial derivatives, right? So you can think of it as a slope of sorts. You can think of it as kind of a conversion factor. It's what you multiply by r changes to get x changes on certain assumptions about theta being constant, for example. Lots of different ways to think about it. For the moment, I want to think about it as a computational tool that's part of our chain rule that we motivated by way of a sequence of, a significant sequence of arguments. Right, so for the moment, in some sense, we did our interpretations a long time ago, and now we're trusting the process that we've created. Is that cool? Does that make sense? Okay, yeah. Okay. All right. Okay, now, of course, that's just that partial derivative. This extra factor doesn't disappear, right? Make sure you don't forget it. It's really easy to mess that up. Right, but you do have to, retain the rest of what you got there, and then the same, morally equivalent process over here when you want to interpret this. I claim it's going to turn out to be that. We're looking at the partial of zy. There it is. With respect to r, there it is. And again, we have two paths. What you might call the x path, which gives you the x term, what you might call the y path, which gives you what you might call the y term, and of course, don't forget to transcribe appropriately. So again, same basic idea, right? And again, something we can read straight off of the diagram because we've appended our diagram appropriately. And because we're relying dutifully on the diagram. Okay. All right. Okay, it's kind of all over with the shouting at this point. We've got some easy partial derivatives to compute again. That's all just again, we already know the formulas for for polar coordinates, so no big deal there. These factors like partial of zx with respect to y. Now again, you might want to worry about, oh gosh, do I have a chain rule? Am I prone to writing down a bunch of nonsense by rewriting that as zxy? And no, not at all. Z is directly a function of x and y. I'm not creating some sort of new imaginary nonsense when I say, I want to take that function, I want to take its x partial, and then I want to take the y partial of that. No composition, no problem. So, perfectly fine. to write that like that, and then you multiply, you gather like terms, etc., and here's your final answer. Okay. All right. So there's a homework exercise that y'all are going to have, which is where you're going to do something highly analogous to this calculation. And the only difference is what you're going to do is going to be partial derivative, second partial, that is, with respect to theta. And that'll change things a little bit. You won't get lucky in this sense of constants like we did here, because those won't be constants. Because if you think about it, what is the partial of x? That is r cosine theta. What is its partial with respect to theta? Negative r sine theta. And it's not a constant, right? It's got thetas in it. Theta is the variable we're taking the partial with respect to. So instead of getting lucky and being able to treat this product by realizing that one of the factors is a constant, instead you're going to have to use the product rule. Now y'all remember the product rule. Just don't forget to apply the product rule when you get to this point in the calculation right here. All right. Okay, again, homework exercise. All right, moving along. Let's talk about a really cool application of this stuff. By the way, this application is why I put this material into the course. So let's recognize for a moment this business about second partials related to the chain rule is not in the book that I recall seeing. I'm pretty sure it's not in the book. Anyway, I don't think it's in the book. And I think that's unfortunate. This is really, really important. This is something that actually is really useful in a lot of ways. And so I used this second derivative stuff a bazillion times when I was taking physics classes way back when. And y'all are going to be taking a lot of engineering classes. They're not that different. So you're going to be using a lot of these same ideas. So, okay. So let's talk about this thing called the Laplacian. Really big deal, Laplacian operator. Really big deal if you're interested in how waves flow or how heat moves, or if you want to understand electrons, stuff like this. Okay, so lots of really big, important topics. Okay, and you'll see how those applications work in other classes, I'm sure. Okay, so it turns out that you can rewrite the Laplacian in spherical coordinates, and it looks like this. That's the spherical Laplacian, we call it. I claim it does exactly the same thing as what I have up in the top equation, the rectangular Laplacian. It just does it in terms of spherical coordinates, which ends up being convenient sometimes. Now, aware, as I am, that does not look like a win. Right? I mean, let's just recognize for the one. You look at these two equations. Which one of these looks friendlier? Which one looks like it's going to be a nicer one to deal with? Nobody's picking the second one. Right? It looks like a nightmare. By the way, that's full confession. That's what I thought when I first saw it. I saw this and I thought, thanks, but no thanks. I'll tough it out with rectangular coordinates. Anyway, before I explain to you where this comes from, I want to show you why it's so much better. I want you to see in action how it's totally awesome. And here's one of those applications we were just talking about. We were talking about the Laplacian, helping you understand, various different things. One of them is it helps us understand how gravitational fields, or more to the point, gravitational potentials work. Gravitational potential energy. And likewise, electric potential energy in each case where you have a single source, right? So either a single point mass or a single point charge. Okay, so how do we understand the resulting potential? And so we're going to entertain as a candidate this function right here. Notice these are the same. It's just, one's in one's in spherical, one's in rectangular. Turns out that's the right answer, by the way. Right? So, but if I want to claim that this is the right answer, I have to show that this function when I put it there, and when I apply to it the Laplacian, I've got to confirm that I get 0. So in order to do this, here are your options. Here are the two different paths by which you can confirm this. One is you can apply the rectangular Laplacian to the rectangular form of the function, plan A, right? And then your other option is you can apply the nightmarish looking spherical Laplacian to the spherical form of the function. Now again, same thing. I claim they're the same things. And which one of these calculations do you want to do? Right? So again, you're going to have to compute and confirm as 0 either this or this. Now I'm going to kind of wave my hands at option 1 there. I think you're going to have to do option 1 as a calculation somewhere along the way in this class. I can never seem to remember where it comes up. I'm pretty sure there's a homework exercise that has you actually compute that. It is a tedious calculation, and it's going to take you a page or so of algebra. And it's something everyone should do once in their lives. I did mine. It's your turn, right? So you're gonna do that calculation. Not so bad, but it's inconvenient. It's definitely inconvenient. So I'm gonna put a frowny face next to this just to recognize that is pretty inconvenient, right? So what I'm gonna do instead is I'm gonna show you how crazy convenient this one is. This one is easier. It's a lot easier. It's so easy, we're gonna do it right now in our heads. That easy. And here we go. You see that we have 3 terms, the last term of which is right here. We're going to apply this operator to that function. The very first part of applying, here, let me just erase, this is confusing. The very first thing that happens when I apply that operator to that function is apparently I need to compute a theta partial of a function that doesn't have any thetas in it. That's a 0. We're done. We walk away with that term. That term's gone. Right? No thetas. Theta partial is 0. Anything you subsequently multiply or operate to 0 is still 0. And so again, that term, 0. Pretty easy. Yeah? Nice. Okay. All right, let's look at the next one. What happens when I apply this operator to that function? Well, the very first thing that happens is I take a phi partial of something that doesn't have any phis in it. Poof, done, gone, 0. Don't need to entertain any of the rest of this because altogether, the very first thing that happens is this turns into 0. And then whatever you multiply by 0, whatever partial you take of 0, whatever you then subsequently multiply by 0 will continue to be 0. Yeah? I mean, this is starting to look pretty good, isn't it? Right? I think this is, compared to what it looks like at a glance, amazingly good fortune. All right, let's look at the last one. Now we are going to have to do just a slight amount of actual effort here. If I take the row partial, that does have a row in it. Okay, so we're going to get something divided by rho squared. Right? And you think about the power rule, old news. Something divided by rho squared, which I then multiply by rho squared, which makes this, what I have outlined in gray, a constant. And if you take any sort of a derivative, I don't even care what, of what I now know to be a constant, any derivative of a constant is 0, and again, game over, and the whole calculation is 0. All right. Oh, I missed the... So all 3 terms are 0. We're done here. Right? As required, we computed this seemingly scary-looking spherical Laplacian applied to our candidate function. We got 0. Equation confirmed. Now, if you want to stick with the rectangular, I suppose, that's, it's not against the law, right? You can, I suppose, but it's a really bad idea. In a situation like this, it's just nobody would do that, right? So now, is this a peculiar circumstance? Is this some rare one-off that only happens in this niche little circumstance? Not at all. Ultimately, what makes this work so well, thinking of this entire question in spherical coordinates, works so well because we're looking at something that is unavoidably, intrinsically, spherically symmetric, right? We got a point source, and it creates gravitational fields that are symmetric. Spherically, like rotationally symmetric in all different directions. So the spherical aspect is intrinsic to the problem. This spherical aspect is intrinsic to lots and lots of problems, right? That's how gravitational forces work. It's how electric forces work. The world's full of round things, right, in short. And so this is a very common story. Yes?
Does that mean we need to memorize the Laplacian for?
I've never memorized it in my life. It's a use as needed kind of thing. I would have to think very carefully about if I were going to make a test question that in which my intention was for you to do the spherical Laplacian. I'd have to think very carefully about how to treat that. So I would either give you the formula or I would let you know in advance, hey, by the way, I changed my mind. I think you need to memorize the spherical Laplacian. Something like that. I wouldn't spring it on you. I've certainly never memorized it. So, yeah. The rectangular Laplacian is hard to forget once you see it, I think, right? So the rectangular Laplacian, certainly eventually you will need to know. And it's so easy to memorize, why not? Okay. All right. Okay, so I hope I've made a sale that this idea of a spherical Laplacian is a good idea. More to the point, that changing from rectangular coordinates to spherical coordinates has its benefits. So let's talk about how do we know this is true? Where did this come from? It doesn't look very true. It looks super weird, right? Okay, so how do we know it's true? And the calculation is very, very tedious, and I don't recommend it. It's like really, really tedious. But I am going to show you strategically how it sort of basically plays out. And I want you to understand sort of what the strategy is, and if the circumstance were to ever arise where you had to, I want you to be able to. I don't want you to actually do it. It's too much tedium. So I'm going to show you an analogous calculation, and that is this right here. So we'll start with this equation. I claim we've already done this. This is a formula on the previous page. We wrote it a little differently on the previous page. This is written currently as a statement about operators. Operators apply to some function. And if you apply these operators as indicated, notice what you would get is this, which is literally exactly this equation. Sorry, missed it. That equation right there. Different notation to be fair, right? But exactly that equation is where this comes from. Now, quick pause. Why do we write it as a statement about operators instead of as a statement about partial derivatives? And well, because in the way I'm writing it here, it's the operator that is actually the thing of interest. Some function z that I would apply these operators to, I'm not interested in any particular z. I'm interested in what's the relationship between rectangular partials and polar partials. And so there is no reason to put the z in there. We can just talk about this as a statement about operators. So heads up about this notation. I know it looks a little weird and a little creepy and mysterious, and don't be intimidated by it. If it makes you feel better to put a little z on there, don't get me wrong, it makes me feel a little better sometimes too, right? But go ahead if you want to put a z in there. I want you to be prepared for the fact that you're going to see things written like this. Okay, when you do the theta exercise, this is going to be that first step, and this will be what you have. And notice, what I have now is kind of a system of equations where the x partial operator and the y partial operator are the variables in a sort of a system that you can then straight up solve for. And when you do that, this is the formula you get for the x partial, and this is the formula that you get for the y partial. And by the way, you can straight up do that calculation yourself. That's an easy little linear algebra thing. You can also, if you just want to kind of confirm, you can take this formula for the r partial and this formula for the theta partial, just kind of plug them in there and then just compute, compute these, and what you'll find is that those are exactly what you get. So you can, rather than solve, you can just confirm, and it's easy to do. No big deal. Side note, while we're here, these end up actually being pretty useful formulas too. These are good to know that these exist. Again, you don't need to memorize them, but it is good to know that these exist because, well, let's see here. Sometimes we will be dealing with functions that, as we just discussed, are very naturally and conveniently written with respect to curved coordinate systems, polar, spherical, cylindrical, whatever. If you have a function that would naturally fit with r partials and theta partials because it's written in terms of r's and thetas, that's a handy way to proceed. If you might, even if what you need is the x partial or the y partial, this tells you how to do it without converting into rectangular coordinates. And again, very handy, much easier in a lot of circumstances. So, good to know that these exist. Okay, so, all right, what happened here? What does this have to do with the Laplacian? And the big idea here is that what we kind of just did is we did some we did first derivatives, but we did some sorts of derivatives of the composition, and then having written those partials down, we then solved for those partials. So we compute the green with the chain rule and then solve for the blue subsequently. That's what we did here. Right? We computed the green with the chain rule and then we solved for the blue with a little linear algebra. Okay. Where this big equation up here comes from is morally equivalent to that. You're going to compute a bunch of spherical partials using the chain rule and get some big formulas. And then you are subsequently going to solve for those partials in terms of the green partials, and therefore you will have computed this in terms of the green partials, and this is what will come out. And again, super tedious. And again, I'm not recommending it. I'm not suggesting you should actually do that. The mechanics on that is super tedious, right? But see how it's strategically the same as what I did here. This is just a lot easier the actual solving is just kind of falls in our lap. A little bit easier in this context. Morally equivalent calculation. Okay. All right. Cool. So moving along. See how we do. Oh, we got lots of time. Okay, on to 2.6. Oh, by the way, while we're at it, I'll point out there's no way that we're going to finish section 2.6 today, and we've already not finished section 2.6 in oh gosh, I've already forgotten the dates. Anyway, the more relevant point, there's no way we are going to finish 2.6 today in this class, and I want to keep both classes on the same schedule of fair game material. You'll notice this from the class schedule that both classes are going to have the same fair game material for the midterms, even though they are different midterms. Right? So 2.6 will not be fair game for the midterm. But it will be fair game for exam 2, and exam 2 is not that far away, so we do have to proceed and we do have to keep going. Okay, here we go. So I want to talk momentarily about partial derivatives. Just kind of I'm going to call it a summary for the moment of partial derivatives. I want to go into the reminders of all of why this is true, but we know that partials are a slope of the graph, and blah, blah, blah details, but it's slope of the graph is one interpretation. Multiplicative factor, especially if you're thinking about the literal point of view on a function. Domain over here, target over here, and if you move in let's say the y direction in the domain, and you want to know the resulting output change in the target, partial derivative, again, appropriate details, it's the multiplicative factor there. Okay. Here's one we haven't seen before, but this is a true statement. A partial derivative is also this little weird expression. I think this is a healthy little exercise to confirm for yourself. It's not a big deal. It's not a hard calculation. Notice what I have here is a composition. I have f of position, and position is a function of t. This is a composition. We're taking a derivative of a composition. If you just write down the chain rule on this, out will come literally the partial of f with respect to xi. So good exercise. I hope you'll give that a try. By the way, the interpretation that I would take on this is that this, and this is just kind of thinking out loud, what this describes is motion that goes through the point A and is moving in the direction of EI, namely is moving in the direction of the xi variable. So this literally describes motion in the xi direction. And the fact that I'm looking at df dt says, yeah, and I want to know how fast the function's changing as I move in the xi direction. So it's pretty easily seen to be, it's pretty much, it is just, it's almost like it's saying the exact same thing that a partial derivative is, just kind of in a different way. So hopefully believable. Anyway, confirm with the chain rule, and that is another equivalent interpretation of a partial derivative. And then here's another one. This is a lot easier to confirm, but again, make sure you can do this. If it seems silly, it really does seem silly here. But if you were to write down the gradient, being as it is full of a bunch of partial derivatives, and then if you dot with EI, which is full of a bunch of zeros, put a 1 in a single position, right? Then you're going to get that corresponding partial derivative coordinate as the dot product. So again, think that through, write it down if you have to, make sure you're clear why this is true. And again, I know it seems silly at the moment. Okay. Now with this established, I'm going to pull a tricky move. This is subtle. First thing I'm going to do is I'm going to point out if all of these things are equal to the partial, then they are also all equal to each other. I don't have to bring up partial derivatives to observe that these four things are all equal to each other. Yeah? Yeah. Now, they're only equal to each other, that I know, because they're all pointing in what I'm going to call standard basis vector direction. So you see the role that the standard basis vectors are playing here. That is part of the deal, right? For the moment, all we know is that these are all different ways to represent partials, but partials, critically, by definition, you got to be moving in the direction of an axis. You got to be moving in a direction of a standard basis vector. So note that dependence. And I think I have this written down here. Yeah, this is only for standard basis vectors. All right. So I'm going to set that aside now for a moment. And let's talk about that. Let's talk about standard basis vectors. What is a standard basis vector? Well, it's a vector that points in the direction of one of the axes. Yeah, okay, but who sets the axes? Right? It is kind of arbitrary if you think about it. Now, just as a real-world example, let's think about the picture I have down here, and you can see I have some level curves drawn. I like to imagine here that I'm on a hike and that these are the contour lines on my topographical map. And I've got some, this two pictures of the same thing. And when I'm out on a hike, I have a location. I exist at a place. I don't think about coordinates very much. I don't think about axes very much, right? Why would I? I guess every so often I got to look at the map or something, right? But axes are not a requirement. Axes are something that we choose. They're something that we make up. Because it's convenient in a lot of cases, you set up axes, now you can talk about coordinates, and that makes it easier to write down things like locations if you can write it as a list of numbers, those numbers being coordinates, those coordinates coming from having set axes. But it's a choice. And how you set up those axes is a choice. It's kind of whatever you want to do. So for example, I suppose I could set up my axes like this, arbitrarily, I guess, right? But you know what? I could also totally set up my axes like this. There's no law that says up has to be an axis or that exactly to the right has to be an axis. That's a bunch of arbitrary, I'm not saying I have a better idea, but it's arbitrary. Well, think about the coordinate system we use on the globe. Right? We're kind of accustomed to north. You got natural, meaningful thing. And again, I don't really have a better idea, but somebody made that up. Right? Here's one. Maybe, call me crazy, maybe we should set up a coordinate system on the basis of how compasses work. That's how you actually navigate. Right? I don't know if you're all aware of the fact that the magnetic North Pole is not at the rotational North Pole. They're off by quite a bit. So, instead of using the rotation of the Earth, and now our compasses are all kind of off a little bit, right? How about we just use the magnetic North Pole? And now every compass is exactly by definition perfect. That would be a different coordinate system. Again, I'm not saying we should, but I'm saying that wouldn't be crazy. Does that make sense? All right. Okay, so if setting axes is arbitrary and therefore, what we call a variable is really kind of arbitrary, this is a bunch of made up stuff, I'm going to make the outrageous suggestion that any unit vector could be a standard basis vector. Right? So for example, let's look at these two vectors here. I've got v and w. Again, these are the same v and w, exact same vectors. And again, this is me, right? I'm that little spot right there and right there. Those are two different directions that I can look on the hill that I'm climbing on, and I don't care about what the map says about which way is the axis directions, right? I'm out in the world, and I'm here, and I'm looking that way, and I'm looking that way. And I don't care about your axes, right? So, is v a standard basis vector? Well, if I set my axes like this, then yeah, v is a standard basis vector. But if I set my axes like this, now no, v is not a standard basis vector. Right? And then, likewise, is w a standard basis vector? Well, with these axes, it's not, but with these axes, it is. So again, it's kind of arbitrary as to what is and is not a standard basis vector. And so, big point, the big conclusion that I want to get to here, any unit vector could be a standard basis vector. Just set your axes accordingly. Does that make sense? It's one of these things that we don't question this very much. We kind of get accustomed to, well, we set our axes and then we do business within that context, that framework that we've set up. Don't forget, that you're not married to that, right? You can totally say, I don't like this axis. I'm going to change my coordinates a different way. And so any vector as such could be a standard basis vector. So let's look back at our result up here. These four things are equal, but only if the unit vector direction is a standard basis vector. Becomes kind of a silly requirement. Every unit vector could be a standard basis vector. Just look at your coordinates a certain way. And so, appropriately viewed, slope of the graph, multiplicative factor, this expression and that expression will always be equal for any unit vector. And if you don't believe me, set your axes accordingly. They become standard basis vectors, and it's all an observation about partial derivatives. Okay. All right. So, here's where we go with that. So reminder, we already agreed slope of the graph, multiplicative factor, this expression, are all equal to each other as long as the vector in question is a standard basis vector, which again, every vector is. Right? So now what we have is, hey, guess what? All four of these things are always equal whenever you have any unit vector. Oh gosh. I want to try to get all this on the screen. Yeah. Any unit vector. It's pretty awesome. Now, we just drew powerful conclusions by not doing any calculations at all, just kind of reminding ourselves about, wait a minute, who's in charge here? Is the coordinate system in charge or are we in charge? Turns out we're in charge, right? Free results. No computation necessary. Now, what are we going to call this? Can I call this a partial derivative? Oh, gosh, I kind of suppose if we wanted to be really, really hard-headed about it, we could, but here's the reality. The reality is, yeah, in fact, look, most of the time we want to do business in a coordinate system, and I don't want to not be able to set a coordinate system to do business because we really kind of need to. So all I'm going to do is take the fact that these things are equal, and I'm just going to give them a different name. We're going to, instead of calling these partial derivatives, I'm just going to call them directional derivatives. That's the big idea. The point being that the unit vector in question defines the direction in which I'm kind of sort of taking a derivative. So thus the term directional derivative. Here's the notation that we use. That's the notation I'm going to use here. It's pretty standard. By the way, there's always a million different notations, and in some other classes you're going to see them written a little bit differently, whatever. But that's the notation we'll use in this course. And, there you go. Directional derivatives. They behave just like partial derivatives. They just are more flexible and can point in any direction you like. Yeah?
They only can be unit vectors?
Yeah, that's a great question. If you take let's flash back to linear algebra class long ago, right? But you can do a change of variables with respect to any basis. Any basis, it doesn't have to be unit vectors. That's true. The problem is, if you don't pick an orthonormal basis, then you're going to change your sense of distance in the domain. That'll change your units. That changes interpretations. Things get weird, and you don't want to do that. So, in order to avoid that kind of nonsense, right, I'm going to say, look, only orthonormal change of basis. Distance is all being preserved and all those problems go away, and the upshot is only unit vectors. Yeah, it's a great question. Yeah.
Is the t variable like the only reason why we make it is to initialize the redirection?
Yeah, that's exactly right. Yeah, it's a tool to help us say I want to figure out what's going on as I move in that direction, and t is what allows me to do that. Yep. Okay. Yeah, neat fact. So, as it turns out, very often you're going to be interested in this expression. Very often you're going to be interested in the scenario where you're at some point A and moving with velocity v, and you want to know how fast some function's changing. It's a utterly routine scenario, right? And here's the good news. There's a very convenient formula for how to compute it. Now, you may recall this came from the silly equation we wrote down on the previous page, seemingly for like obvious nonsense. Why would I write that down? But here we are. Now it's handy. Now I see that that's the computational formula to get at this abstract question of, hey, how fast does the function change? And by the way, of course, don't forget, when you compute this directional derivative, you can interpret it as the slope of the graph. You can interpret it as a multiplicative factor. Okay, now there's one other little detail I want to get to before we do some examples, and that is going to get down to this multiplicative factor business. So let's talk about how would I interpret this multiplicative factor. The thing that I'm going to multiply by input changes to get output changes, right? Looking at these equations here, what notation would you think would be the convenient, natural, satisfying notation for the thing that multiplies by these green things to give it these blue things? And I propose what I have written down there, that this multiplicative factor, very naturally written as DFDS, because again, think about single variable chain rule and the sort of the cancellation, and it's all a little fishy and bogus, but it's in the single variable context that we're looking at here. Actually, it's basically fine. All right. So heads up, this is another interpretation. I guess you might say another take on this interpretation of the directional derivative. The directional derivative, in addition to being the blah, 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 it's also DFDS. It's the rate of change of your function with respect to distance traveled in the v direction that you've indicated. Okay. All right. Let's see some examples. All righty. We've got. Let's see here. We've got some function of position, and the question says, let's compute the slope of the graph. Details given, but the question says slope of the graph, and going back to the previous page, if you want to compute the slope of the graph, that is one of our very first properties of the directional derivative. So if you're interested in the slope of the graph, cool, compute the directional derivative. And you'll notice that's the very first thing that I write down here. Slope is the directional derivative. But wait a minute, how do we compute directional derivatives? I mean, plug and chug. Let's, rubber meets the road. How do we actually do this? Well, directional derivatives, the most convenient computation's right there. Gradients are easy to compute. Dot products are easy to compute. I think that's the way to go, right? So, dot product with the gradient. Next thing I write down. So there you go. Now, there's there's two little asterisks here. Of course, the gradient is a matter of various partial derivatives. You plug in, of course, the point that you're given. That's where you evaluate partial derivatives. Yeah. Here's the first little subtlety. Keep in mind, if you want to make this interpretation, if you want to make this interpretation that directional derivative will compute a slope, then this vector has to be, that vector v has to be a unit vector. And again, it's a big deal. Things will get messed up if it's not a unit vector. This property is not true if that v is not a unit vector. Okay. All right. So, was I given a unit vector? Sadly, no. Okay, so right, fine. Well, I want to go in the direction of this given vector. How do I find a unit vector that points in the same direction as a given vector? Well, again, easy, right? That's we have this old formula from chapter 1. You may recall from linear algebra class. Divide a vector by its own magnitude. Boom, now you got a unit vector. Is that cool? So just don't forget to do that, right? There's this tendency to kind of rely a little too much on the alphabet, and it says V. The formula has a V in it, and I'm given a V, and so I guess I must take this and plug it into there. And of course, that's silly, right? That's not at all how it works. People will make inconvenient notational choices sometime, and you're responsible for making sure you understand what the formula is actually saying and applying it appropriately, and not just relying on the alphabet. So heads up about that. So you notice, as I have in the calculation here, it is the unit vector u indicating the direction for the directional derivative. Therefore, it is the unit vector u that does the dot product with the gradient, blah, blah, blah. Okay. All right, so next little tricky bit here is a point of language. And let's note what we have here. I'm just going to kind of draw a picture. We're at this point, 3, 1. It's about right there, let's say. And we've got this vector given that's 3, 4. Oh, let's see. I think I used 3, 4 like that. Okay, so 3, 4 would be something like so. Wait a minute. We want the direction of that vector. That is the unit vector that's in that direction. So here's sort of a color-coded picture of what we were given and what we inferred. Okay. Here's a landmine mistake that a lot of students make. I see this on the regular. A lot of students will mistakenly misinterpret in the direction of, let me actually circle a little bit more. In the direction of the vector, a lot of students will misinterpret that as being toward the point 3, 4, and that's no good. A vector indicates a direction and a magnitude. The way the question is phrased, it says, look, we've got this vector. I want the direction that direction and magnitude are talking about. You can't say, I'm going to interpret the vector as a point and then head toward that point. Not the same thing. And you can explicitly see, if you were to interpret this as being a point, that point would be about there. If you were to head toward that point, check it out. You're not going the correct direction. Everybody see the mistake and how that leads you in the wrong direction, literally? Okay. So again, heads up, be careful with the language, and don't misinterpret. Okay, moving along. Another example, different scenario. Here we have temperature given as a function of position, such as in this room, right? I mean, it's warmer by the light bulbs, colder in the corner in the shadows. Temperature is a function of position, and perfectly reasonable real-world scenario, we're at a certain point, and being at that point, I might want to know, look, if I head in the direction that vector points, how fast is the function changing? How fast is temperature changing? Per unit distance. I haven't decided how fast I'm going to move yet. Don't nail me down as to what my speed is, but just per inch that I move in that direction, how much does the temperature change? Reasonable question. Okay. So again, what we've been asked to compute is one of our interpretations, sort of a rephrase of this interpretation of what a directional derivative is. And so again, that's the first thing we're going to write down. The thing we're interested in, that dTds, is that directional derivative. And again, We're going to compute the directional derivative with the dot product because, well, of course, right? Super convenient. Hard to beat that for convenient. And again, there's the little asterisk. Don't forget that the direction of a given vector is that vector divided by its magnitude. And again, don't forget, you only get these interpretations if you follow the rules and only use unit vectors. Is that cool? Is everybody happy? Pausing for questions. All right. Okay. Now here's an awkward reality, and so y'all remember how frustrating it is. Back in chapter 1, we were talking about spherical coordinates, and it's just maddening. But the world cannot seem to universally agree on what to call the spherical coordinates, and some people call them rho phi theta, and other people call them r theta phi. And believe it or not, other people call them different things. So, oh my God, so confusing, super annoying. We have another one of those situations on our hands here. And again, not my fault, right? I didn't do it. I'm the bearer of the bad news. So, believe it or not, there is a different point of view on what the word directional derivative ought to mean. And here it is. Sometimes this unit vector requirement is removed. Can you just do that? Oh my gosh. Well, yes and no. The concept changes very significantly. And let's see, I'm going to have to scroll to zoom here. Okay. I think I didn't work with this. If you remove the unit vector requirement, you no longer get any of these properties. It's no longer going to give you slope of the graph. It is no longer going to be the multiplicative factor. It is no longer going to be DFDS. All that's out the window. Okay, well, yeah, but why would anyone want to do this? Rhetorical question. And the reason why is this is still a pretty natural question that I want to ask. It's still a perfectly reasonable question to say, hey, look, I'm at the point A and I'm moving with velocity V and I want to know how fast the function's changing. Perfectly reasonable question, crisp and convenient formula to compute the answer to the question. It makes sense that we would want to have a name and a notation for this very natural scenario. Okay, all right. So, bummer. Oh my God. So we have this situation then where this word directional derivative means different things to different people. In this class, we are going to stick with the book's definition, right? The one that I've been pitching this whole time. In this course, unit vector required. The word directional derivative in this course always means, with the understanding we're talking about a unit vector. The reason I'm telling you all of this is because you will eventually not be taking this course. You will eventually have finished this course and you'll be out in the real world. And out in the real world, different people will mean different things, and you need to be aware of that, right? You need to be on the lookout. And if somebody's using the term directional derivative and they're applying it to non-unit vectors, you need to be aware that that's a possibility. You need to notice it when it happens, and you need to correspondingly make sure that you remember not to try to pull any of this nonsense because it doesn't work anymore given their usage. Does that make sense? So heads up. Again, I wish it weren't this way, but this is just a disagreement in the use of that term. By the way, just full disclosure. Outside of Math219, I'm one of these people. And there's really good reasons for it. Much better than what I've shown you here of these things being natural anyway. There are some excellent reasons to want to be able to use this term in this way. So, but in Math 219, we're sticking with the unit vector requirement, just to be perfectly clear. In Math 219, only unit vectors, and then that and that and that and that and that are what the directional derivative is. Okay. Sorry for the state of reality. Okay, moving along. Okay, so this is a lovely little discussion. We're going to discover some fascinating properties of the gradient vector unexpectedly. It's going to show up unanticipated. Right? And the way it's going to happen is we're going to ask a natural question, perfectly reasonable question, and as we answer that perfectly reasonable question, well, again, the gradient's going to end up showing up. So here we go. The reasonable question I want to ask is, suppose you have some function like this, differentiable function. You're looking at some point A in the domain. Okay. And you want to entertain now, from that point A, you want to entertain all possible unit vectors. In other words, all possible directions from which you might move from that given point. Don't worry about how fast you're going to move. We'll worry about that later, right? Let's just think about the directions themselves, thus unit vectors only, right? So of all these possible directions, I mean, a pretty reasonable question to ask is which one will maximize the directional derivative? In other words, which direction should I start walking if I want my function to increase as fast as possible? Why would we ever, where does this question come up? Well, I mean, maybe this function is representing engine efficiency. And naturally you want to increase your engine efficiency. And well, if there's a bunch of different ways that you can tweak the parameters of the engine that you've designed, how should you tweak them? Well, you should tweak them in whatever direction is going to make the engine efficiency increase as fast as possible. Or at least that's certainly a consideration. Okay, so very natural questions. Everybody buy how this is a natural question? Okay. All right. Well, what terminology are we going to use on this? And I can give you a couple of different takes. One is I can interpret this directional derivative as being a representation of how fast the function is changing with respect to distance. So df ds. This is an expression that says how fast does the function increase. And if I want the direction that maximizes that, right, the direction that maximizes, whichever one it's going to be, I don't know, maybe it's this one, whichever one maximizes, that's the direction that makes the function increase the fastest, or as you might say, the direction of fastest increase. Right, that'll tell us which direction is making the function increase the fastest, thus this one. Okay. Now, on the other hand, there's a different way to think about this entire question. If you were to think of the directional derivative as telling you the slope of the graph. Now again, directional derivatives tell you slopes only for graphs. And again, you got to keep that context in mind, right? It's got nothing to do with level sets. It's got nothing to do with any of various other kinds of pictures we might draw. If you want to think of this as being the slope of the graph, if you want to find the direction that maximizes the slope of the graph, I think this is a pretty reasonable terminology. You're trying to find what direction to go that makes the slope of the graph as steep as possible, right? So there's going to be downward in some directions and upward in some directions. Which one makes it the steepest? How about direction of steepest descent? Reasonable terminology. Everybody on board? Okay, so a heads up for both of these terms. Again, a little cultural point. Let me make my pitch first. I think this is the most general take to think of directional derivative in the most general terms. This doesn't assume anything about what kind of a picture you're looking at. You could be looking at any picture at all. You could be looking at no picture. just wanting to know, hey, look, I'm trying to make the function increase as fast as possible, no picture required. So this terminology makes sense in all contexts, right? This terminology down here doesn't. This terminology here only makes sense if you're looking at a graph. So my preference is the green one, direction of fastest increase. That's what you're going to hear me say. Outside of Math219, you're going to hear direction of steepest ascent more often, and it just bugs me because it doesn't make sense most of the time. So heads up on that. We'll answer this question next time. See y'all later. Have a good one.